Today we're going to learn chapter 2, resistive circuits, part 2. We're going to learn single loop circuits, single node pair circuits, and also how to combine resistors, and also circuits with series parallel combinations of resistors. First, let's look at a single loop circuit. So over here, I provided a single loop circuit. This circuit contains like 1, 2, 3, 4, 5, 6 elements, and they're all connected together to form one single loop. This is called a single loop circuit. So let's review the concept before we move on. So this circuit has 6 branches. Every element that forms one branch, and between elements there will be a node. So we have in total 6 branches, and this is a node A, B, C, D, E, F. That's 6 nodes, one loop. If we apply KCL to all the nodes, for example, at node A, the current goes through the element 1, I1, assume that it goes upward. This is the direction that I assigned. That will be equal to the current leaving the node, say, this is my current I2. And the same thing for all the nodes. So basically, if we apply KCL to all the nodes, and we will have the answer I1 is equal to I2, that is equal to I6, that is equal to the current going through this loop, right? So this is a single current going through this loop. They are the same. If we apply KVL to this loop, KVL tells us that the voltage drop by following a closed loop that adds up to 0, right? So we do that, we say like a voltage drop on element 1, we call it a V1. The voltage drop on element 2, that is V2. The same thing for others. So we will get a conclusion V1 plus V2 plus all the way to V6 is equal to 0. So KCL and KVL describes all the relationships that we need to know about this circuit. So let's look at one example. This example is called a voltage division, and this is a direct application of a single loop circuit. Let's look at this circuit. In this circuit, we have a single loop with 3 elements, 1 power source, V, as a function of T, and 2 resistors, R1 and R2. The voltage drop on this resistor R1, that is a VR1. The voltage on this resistor R2 is a V sub R2. So from the previous conclusion, we already know that the current through all these elements are the same, that is equal to this current IT. And the voltage summation VR1 plus VR2, that is equal to the voltage applied here, that is VT. We also know that according to Ohm's law, the VR1 that is equal to I times R1, VR2 that is equal to I times R2. And we can find the voltage ratio on the 2 resistors that is equal to their resistance ratio. The I will be canceled. If we just submit this value to this equation, I will be canceled, right? So combining the two, so VR1 plus VR2 that is equal to V, and a VR1 over VR2 that is equal to R1 over R2. We can find VR1 that is equal to R1 divided by R1 plus R2 times V. And similarly, VR2 that is equal to a similar form, but with R2 on the numerator. So what I want to point out about this result is basically the physical meaning behind it. By looking at this example, we have 2 resistors in series. The voltage on one resistor, VR1, is part of V. And the portion depends on the ratio of R1 and R2. Or you can say the ratio of R1 and the total resistance. So a bigger percentage of this one resistor compared to the overall resistance, the higher voltage drop will happen on this resistor. The same thing for VR2. So this is called a voltage divider or voltage division. Now let's look at a practical example for power transmission. We have a power line. Here we generate a high voltage power. So that is a 400 kilovolts. And this is transmitted to the user end. The user end is represented by a load, R load. R load is equal to 183.5 ohm. And we know that like for any power line, there will be resistance no matter which material that you use. So for this wire that has like a resistance of 0.04125 ohm per mile. And in total, we have 400-mile transmission line. If we look at this circuit, there is a resistance in the power line, and there is some resistance from the user side. So we can simplify the circuit to be a circuit like this with one power source with two resistors in series. And this resistor will represent all the resistance of this network. So we did the calculation for this power line that is equal to this much per mile times 400 miles. So that is 16.5 ohm. So now we have a circuit like this. So I can calculate the voltage on the load end by using the voltage divider. So the voltage on the load, that will be equal to the resistance on the load divided by the total resistance times the total voltage applied on these two resistors. Then we can also calculate the voltage drop on this resistor. We have 16.5 ohm, and if we calculate the voltage on that, that will be equal to this 16.5 ohm divided by the total resistance, the same, times Vs, 400 kilovolts. You can do it that way to find the voltage drop on this power line. Let's move on to the power calculation consumed by the power line. So there are multiple ways to calculate the power consumed by a resistor, right? So we basically abstract this power line by a resistor. So you can use I squared times R. You can use V squared divided by R, right? You can also use the current I times the voltage drop. So there are three different ways that you can calculate the power. So over here we use I squared times R. The current I will be equal to the current going through this single loop, Vs divided by the total resistance times R line. We can find the power consumption that is 66 kilowatts. And to deliver a fixed power P generated, why higher voltage is preferred? So let's look at the power consumption by this line. We learned that is equal to I squared divided by R line. The current I can be also calculated by using P divided by the voltage. So the higher voltage that we have, so if P is fixed, the higher voltage that we have, there is a less power loss during transmission. All right, let's look at the next topic, single node pair circuit. So over here I have a single node pair circuit, and there is only one node pair. So this is one node on the top, and the second node is down here. This is one node, although they have like a different connection points, because node is defined as the conjunctions between the elements or the branches. So for this single node pair circuit, we want to find out the relationship between their current and voltage. So again, we only have two laws to use. One is Kirchhoff current law. The other one is Kirchhoff voltage law. So if you apply KCL to this circuit, there is only one node pair to look at. So if we look at the top node over here, we can find that the current goes into this node, I, is equal to the current leaving this node. The current leaving the node, which is I1 plus I2 plus I3 plus I4, right? So that is the relationship between their currents. Next, the KVL tells us the relationship between their voltage. There are multiple loops over here. If we apply KVL to this loop, so we know that a voltage V that is equal to V4. And you can also look at it from the definition, because the voltage here, that is the voltage between these two nodes. So we only have two nodes, so it means everything between the two nodes, the voltage drop will be V. So you can look at it from two different ways. One is the definition, the other one is a KVL. And at the same time, Ohm's law tells us that the current in each branch that is equal to V divided by Ri. So let's look at one simple example by looking at a circuit with only two branches. So if you have a circuit with two branches, the overall current going through the network is I, and it has two branches, one is R1 and the other one is R2. And the same thing as what we did for the analysis, we know that the current going through each branch that is equal to V over Ri At the same time, the current I that is equal to the summation of the current, and at the same time, the voltage V1 and V2, they are the same. So V1 is equal to I times R. I1 times R1, V2 is equal to I2 times R2. The same thing, you can also use the definition, say this is the voltage drop between these two nodes. If I follow any branch between these two nodes, that will be a voltage drop will be the same. So the voltage drop from here to here, by looking at it from this branch, that is equal to I2 times R2. The voltage drop from here to here, by looking at this branch, it will be I1 times R1. So you can also get that. Current I2 into this KCL equation. So I2 that will be equal to V divided by R2. We submit it into that equation, we'll be able to solve I1 and I2. So we find out that I1 that is equal to R2 over the total resistance, R1 plus R2 times the overall current I. So it makes sense, right? Look at the physical meaning of this. So the current in one branch depends on the ratio of their resistance. So the larger resistance you have on the other branch, basically like this branch will try to prevent the current flows from here. It means the larger current you will have on the first branch. So I1, that's why I1 is equal to R2 over the total resistance times I. And on the other hand, this is the same. You only need to know one, you can get the other. If you just switch 1 and 2, then you'll be get I2 is equal to R1 divided by that. The discussion on the single loop circuit and single node pair circuit that will help us to get to the conclusion for a combination of resistors in series and in parallel. So let's look at one example for where we have two resistors in series. And we already know the current flow through the two resistors will be the same. That is equal to the total resistance divided by the two. And assume that we have an equivalent circuit. And this equivalent circuit only have one resistor. This resistor will be equivalent to that. So when we say equivalent, it means that if I apply the same voltage source, I should be able to see the same current compared to the previous network. If we want to keep the current to be the same and the voltage divided by this resistor have to have the value of R1 plus R2. So this is why for two resistors in series, the overall resistance for that is equal to R1 plus R2. In a practical application, you might see the resistor in series, but I probably put it into different forms. And here are all the examples that shows you like resistors are in series. One resistor connect to the other resistor. One resistor connect to the other resistor. The same here, the same here, and the same here, and the same like that. So let's look at a resistor in parallel. So the same thing, like assume that we find a circuit that is equivalent to that. It means that if I apply the same current source, that I should see the same voltage drop. If I apply the same voltage source, that I should see the same current. And then we'll find out the current in the first circuit. If we find the current here, the IOT that is equal to V divided by R1 plus V divided by R2 plus onto V divided by Rin. If we look at the second circuit, the current through that branch that is equal to V divided by R. So when I put it side by side, the V will be canceled. So you leave us 1 over R on the right hand side. That is equal to 1 over R1 plus 1 over R2 plus all the way to 1 over Rin.